will now study problems in wetting, and we apply these ideas to determine the shape of a drop. In particular, we'll be looking at two problems in the next couple of lectures. We'll be looking at the shape of a sessile drop, and then we'll also be looking at the shape of a puddle. The shape of a puddle requires us to understand what is the thickness of a puddle, so that when we pour some water on a surface, we want to understand what is the extent, what is the radial extent of this puddle. Okay. We'll be looking at problems of this nature. We'll be using the tools that we've developed in the last couple of lectures in today's lecture. So let me quickly recap what are the kinds of things that we have seen in the last few lectures. We've looked at problems in energy minimization, where we took an energy functional and we used the Euler-Lagrange equation and determined the shape of a static meniscus. In the previous lecture, I also discussed a new powerful technique called the method of Lagrange multipliers, where we can also apply constraints. If you have to do a minimization problem, but with a constraint such as known volume of a droplet sitting on a surface, then the constraint of the fixed volume can be applied using the method of Lagrange multipliers. Now, some of these problems can be loosely categorized as problems in wetting. That's because we want the nature of the wetting, meaning how the surface, the liquid gas surface, how this interface meets a solid, will also determine the shape of the interface in a variety of problems. Now, wetting is a very broad topic in itself. We could have a variety of subcategories in wetting, which is you can have problems of wetting of a liquid on a rigid surface, where the surface can be absolutely flat and smooth. You could have a surface which is actually rough. And finally, you could also have a surface with chemical heterogeneities on the surface, such that the contact angle at different locations on the surface is different. You could also have problems in wetting on a soft solid, where the surface, because of the presence of the droplet, the surface basically deforms at the contact line. We could also have dynamic wetting problems, where the motion of the fluid will also determine the contact angle. So these problems also come under the topic of dynamic contact lines. This is a topic that we'll be looking at towards the end of the course. In today's lecture, we'll be primarily focusing on the static problems. We'll first look at the new parameters such as the spreading parameter, which tells us what is the nature of the wetting that one is likely to see. And then we'll apply the tools that we had developed earlier, such as energy minimization, the Euler-Lagrange equations, the method of Lagrange multipliers, to determine the shape of a droplet in the absence of gravity. We'll introduce gravity later when we look at the shape of a puddle. So let us begin by looking at what would happen if a droplet is brought near a surface. So consider a liquid droplet. This is a liquid drop. That is brought near a horizontal surface. Now, there are two possibilities. So the first possibility is that the liquid completely wets the surface. And this scenario, we can call it total wetting. You could also have a situation where the droplet doesn't fully wet the surface, but then forms a sessile drop on the surface. This is referred to as partial wetting. Now in the case of total wetting, we have a thin film on top. And in the case of partial wetting, we have a sessile drop. Right? Now in the case of partial wetting, we also have a finite contact angle. You can call it as theta e. Other alternatives would be theta e can also be written as theta y to say that it's a Young's angle. And then we also will have sometimes also referred to as theta s to represent that it's a static contact angle. Now these are all symbols that are used in the literature. Now in general, when we have partial wetting, then if theta e is less than pi by 2, then we refer to surface as hydrophilic, and if theta e is greater than pi by 2, then we refer to the surface as hydrophobic. Now note that we are using the words hydrophilic and hydrophobic to suggest that the liquid is water. It need not be the case. We could have other liquids, and the general idea still carry over to other liquid and solid combinations. Now we'll define a few important terms. Now there are two possibilities that we have here. So the one possibility is that you could actually have a thin film that forms. We'll call this as configuration 1. Or you could have a sessile drop form or a partial wetting that happens. This is configuration 2. So we want to find out, is there a way for us to predict which of these is likely to occur when you bring a liquid droplet onto a solid surface? Okay. Now for this, we need to understand the nature of interactions between the various materials here. So we have the solid, then we have the liquid and the gas. Now, if you have three materials or three parts to the problem, we want to determine what is the surface energies of any two combinations at a time. For example, we want to determine the relationship between the surface energy of the solid gas vis-a-vis the surface energies of the liquid gas and the solid liquid. Okay, so we will first define these surface energies, and we can come up with a parameter which will tell us whether we are likely to see total wetting or partial wetting. So for this, let us define the energies. So we'll define the parameters as follows. So we'll say gamma Sg. Okay, this is the surface tension of the solid, and or this is nothing but surface energy per unit area of the solid. Now typically in most cases when we refer to a gas, the gas is usually air, so you can simply say gamma S. This is also acceptable. Okay. Then the other energy that we want to know is gamma Lg. Okay, and this is also nothing but just gamma L or simply gamma. Okay, this is the surface tension of the liquid or surface energy per unit area of the liquid air interface. In the previous case, gamma Sg represents the surface energy per unit area of the solid air interface. And finally, we have gamma Sl, which is surface energy per unit area of the solid liquid interface, right? Now what we will do is, having defined these three surface energies, now we can define this a new parameter called the spreading parameters. Okay, so How do we do this? We say, let us first examine the free energies of the two configurations. Okay, so we have two configurations, 1 and 2, and we want to determine the free energies of these configurations. Okay, so we'll define a parameter. And this parameter is represented by the alphabet capital S. Okay, and this is difference in the free energy of the of the dry substrate. Dry substrate meaning just the solid. Okay, dry substrate. Substrate here is a solid. Difference in the free energy of the dry substrate with the free energy of when a thin film has formed. Let's look at the situation configuration 1. So in configuration 1, before you place the droplet, you basically have just a dry solid surface. So the surface energy of that configuration is just, we'll call it as E dry. So we'll say this quantity is just E dry. Now we'll ask, what is the difference between what has happened after the solid has formed? After the solid has formed, now we have two surfaces that we have formed. We have the solid liquid interface. So I'll represent this here. This is solid liquid interface, or solid liquid surface, I'll call it. And this is liquid gas surface, right? We have two surfaces. In place of one, we have now created two surfaces. So the energy, free energy after a thin film is formed would be nothing but the free energy of the thin film plus the substrate, right? And this is nothing but the free energy. If I calculate all these as per unit area, then this would be gamma S. That's just the surface energy of the solid gas surface. Gamma Sg, let's call it as gamma Sg for now, minus the thin film. Basically you're creating a surface between the liquid and the gas, that is gamma Lg liquid gas, plus we have gamma solid liquid, right? And this can sometimes also be written as gamma S minus gamma L plus gamma SL, or simply S would be gamma S minus gamma plus gamma solid liquid, where gamma is the surface tension of the liquid. Right? Now, if this quantity is more, if this quantity is positive, if S is greater than 0, then what does it tell you? It tells us that the surface energy of the free energy of the dry state is more than the free energy of a configuration 1 where we have a thin film that is formed. So by forming a thin film on the solid surface, we have lowered the overall free energy of the system, and therefore it is favorable. So in other words, if this happens, then forming a thin film reduces the overall free energy of the system, and it means total wetting will occur. This is configuration number 1. Okay, complete or total wetting will occur. And if S is less than 0, then formation of a thin film is not favorable. Therefore, you will have partial wetting. This is configuration 2, right? And this parameter S is called the spreading parameter. S is referred to as a spreading parameter. So let's again take a look at what I'm saying here. So in configuration 1, formation of a liquid film lowers the overall free energy of the system, and therefore the spreading parameter as defined as the difference between the free energy of the dry state minus the free energy of the state of configuration 1, where we have the thin film formed on the solid, and we also take the surface energy of the solid liquid interface. If there is a net reduction in the energy, and this suggests by saying that S is greater than 0, then S is greater than 0, then we have a total wetting that is favorable, and when S is less than 0, we have partial wetting. Okay. Now, so one of the key things that I wanted to do in today's lecture is to introduce you to this parameter called the spreading parameter. Having done that, we'll also look at another important relationship. Now, in the last, in the sessile drop, in the static meniscus discussion, where we applied the energy minimization, and we specifically focused on the boundary condition, then we derived, one of the contact angle conditions that we got was referred to as the Young's law. The Young's law basically was obtained in terms of the three surface energies that are present in the problem: the surface energies of the liquid gas, solid gas, and the liquid solid surfaces. Now we can also arrive at this using a force balance. So Young's law and force balance at a contact line. So let's consider a droplet on a surface. S clearly has to be less than 0 because we have partial wetting, and we have an angle which I called theta E, right? Now let's examine a small region in the vicinity of this contact line. So let's examine a small region there. Okay. If we examine the small region, what we have is a small wedge. And along this wedge, we have three surface tensions. We have the liquid gas surface tension, which you can simply call it as gamma. Then we have the solid gas surface tension, which is gamma S. And finally, we have the solid liquid surface tension, which is gamma SL. Please don't, these arrows are not to scale. I'm just trying to show the directions. Now let's look at the angle that we have here. This is my angle theta E. Okay. So if you do a horizontal force balance, would be gamma solid liquid plus gamma cos of theta e, that's the projection of gamma along the horizontal. This would be gamma s, and therefore I have cos of theta e would be gamma s minus gamma solid liquid divided by gamma, right? And we can now write this in terms of the spreading parameter. If you recall, the spreading parameter was defined as gamma s minus of gamma plus gamma SL. So I can basically now define this as, recall, S is nothing but, I'll write S in a slightly different way. It is S is nothing but gamma S minus gamma SL. This is the surface energies, difference in surface energies of the solid and the solid liquid interface, minus the surface tension of the liquid. That's gamma, right? So therefore I have gamma S minus gamma SL is S plus gamma. Okay, and therefore I have cos of theta e, the cosine of the angle at the interface at the contact line, is nothing but the numerator essentially can be replaced with S plus gamma by gamma. Correct? Now the equation is only valid if S is less than 0, right? So if S is less than 0, only then can you have a cosine of theta e. The numerator cannot be larger than 1, and if S is greater than 0, then the numerator becomes larger than the denominator, and cosine of an angle cannot be larger than 1, and therefore the equation will have no physical meaning if S is greater than 0, right? So for S greater than 0, we should note that there is no contact line. So this force balance that we have done here, this force balance assumes that we are forming there is a contact line, and we are doing a force balance in the vicinity of the contact line. But if there is if we do not have a contact line, this force balance itself is invalid. And when do we have that? When we have total wetting, where there is a thin film that is completely covering the solid surface, and therefore in such a scenario this is not valid. Okay. Now what happens in the vertical force balance? The vertical force balance is, there is a component of the, we'll call this as R. There is a component of the surface tension force vertically up. So what we have now is gamma sine of theta e minus R is 0. So in such a case, the vertical component of the force is actually balanced by the reaction from the solid, right? And if the solid is a very soft solid, then you can actually have a deformation of the solid. For example, for a rigid solid, you can have a situation like this. This is rigid, and if we examine this region, this is a rigid solid, and if we examine this region here, then what we see is, we see a flat interface then call this as theta e, right? But when you take a soft solid meaning its elasticity also comes into play. You have an interface like this. again, if we examine this region very close to the solid, then what you find is that the solid can deform. So the solid deforms near the contact line, and the amount by which it deforms depends on the elasticity of the solid as well. We won't be able to go into this, but this comes under you can broadly problems of this nature come under the category of elasto capillary problems, where the elasticity of the solid plays a role. You can say elastocapillary, elastovetting problems. Okay. Now we will concern ourselves currently with only a rigid surface. Okay. So what we have basically done, to quickly summarize what we have seen, is we have determined a parameter called the spreading parameter, and I think it's worth putting this in a box here. We've defined a parameter called the spreading parameter. We said that if S is greater than 0, the spreading parameter, then we have total wetting, and if S is less than 0, then we have partial wetting. Okay, and then we also related the contact angle at the contact line, the static contact angle or the equilibrium contact angle, theta E, to the spreading parameter, right? So essentially cosine of theta E turns out to be S plus gamma by gamma. Okay. Now we will consider a situation where we have a sessile drop. We will take it up in the next lecture, but the idea is as follows. We have a horizontal plate. We have a droplet of a known volume, let's say V. Okay, clearly S is less than 0. So what we want to do is we want to write down the we can write down an expression for the surface energy. So that's one parameter. The other parameter is we have the volume V. Okay, there are two quantities, right? So once we know all these quantities, we can define an auxiliary function, auxiliary or a Lagrangian function. We'll call this as L. This quantity would be the surface energy minus the lambda times V, where V is the volume. Okay, why do we do this? Because the problem statement is as follows. Obtain the shape of the drop of a sessile drop subject to a volume constraint. So we'll take this up in the next lecture, where we'll be looking at we'll be using the tools of the method of Lagrange multipliers and the Euler-Lagrange equation. We'll take this auxiliary function and we can directly invoke the Euler-Lagrange equations to do an energy minimization. Recall that the method of Lagrange multipliers allows us to apply the derivative test. That is, apply the derivative test for a quantity called the Lagrangian, where the constraint has automatically been taken into account. Okay, so we'll see this in the next lecture. I'll see you around. Thank you.